Cool.
Welcome back to lecture 18 of CS 136, Deep Learning for Visual Data. So a couple of announcements. Quiz 7 is due tonight. Quiz 8 has been released. It's due next Monday. Quiz 8 is covering GANs 1 and GANs 2, which is today's topic. Homework 3 is due this Friday. Homework 4 will be released sometime next week, which will be due at the end of the semester. Yeah.
Cool. All right. Hi, everyone. My name is Peter. I'm a fourth year doing a one-year master's. Last week, you heard from Steven about GANs, and we're going to expand on some of those ideas, talk about some more detailed architectures and some challenges in training these things. This is my first time lecturing for MLab, so you should definitely ask questions if anything is confusing, and also bear with me if things don't make sense this time around. Highly encourage you to just interrupt me if you have a thought. Yeah. Cool. All right. So we're gonna first talk about using GANs for computer vision, in particular, thinking about some of the harder problems that might come up when we do this in practice. In particular, like upsampling becomes tricky here. Then we'll talk about 3 particular variants of GANs in computer vision that each try to solve different challenges or achieve different goals for improving our GANs. All right. So, but to begin with, we're going to build off of last week, where hopefully we've talked about the basics of why this generative network and discriminative network adversarial setup helps us create interesting images that remain close to some distribution we want to approximate. We've already talked about how for the discriminator, we can just plug in a conventional convolutional neural net, where the idea is that we can take an image as an input and then downsample with convolutions, and then eventually achieve an image that has lower width and height, and instead more channels, and then finally perform some classification head at the end to pick what class is it, what label do we want to learn. We've also discussed how there's different deep learning tricks, things like pooling, norms, etc., that can help us to achieve better performance and build us a more powerful discriminator. The trickier part is thinking about the generator, because remember here that we want to go from some kind of latent space, some noisy random variable that might not be very high dimensional, to an image, right, which is probably going to be a very different dimension overall, and it's not clear how you connect the two. We could so let's start with the downsampling, where the idea is that we conventionally will just use vanilla confnets to downsample. This diagram below is might look familiar, but the idea is, again, just to have some module that goes around and pulls together the shaded areas below, and this filter can decrease the size, make the image smaller. Upsampling gets a little trickier, and we can borrow some ideas from downsampling to help with this. But to begin with, you might imagine that if I want to get from a very small thing, right, something that might have only width 1, height 1, to a bigger image, I could just do something trivial here, which is just I don't know, let's just copy everything 4 times. Something we might just call nearest neighbor sampling, where the idea is each 1 by 1 grid can become a 2 to 2 grid. And so this image here becomes this image here, 1, 2, 3, 4 becomes something that looks like this, right? Anybody have a criticism of this? Again, reminder that we want to get from something that looks like noise to a realistic image. I guess a basic problem is that you have no increase in resolution whatsoever from this up front, where you have the same exact blurriness. It's just a bigger blurry picture. Right? This is what happens if you just I don't know, zoom further in on something that wasn't very high res to begin with. And so this kind of doesn't really help us introduce more granularity into the image or produce something that might look realistic. And so while you could do some other things like convolutions to improve this, there are some more direct approaches to upsampling that might help us. There's 2 ideas we'll talk about. The first is the idea of bilinear upsampling. You might already have the intuition that in this previous setup, you don't want these sort of discrete hard boundaries where you just have like a 3x3 block here, a 3x3 block here. You might want something that's more smooth and introduces like more interesting kind of cells that are differentiated. And bilinear upsampling is just doing exactly this, where the idea is you do actually duplicate the original cells, original pixels, but then you'll take a mean or like average between all the stuff around each new created cell and pixel to pick your new color. And so you can visually see that this new version of this upsampled image is sort of what you might get if you just took this previous version and then did a sort of average pooling layer around it. And that's essentially the idea. Questions, thoughts on this? Cool. A second idea that's also inspired by our GAN sampling approach is a transpose convolution, which we'll also call a deconvolution. Where the idea here is that if you add enough padding around the original image, then your traditional convolution can actually function as an upsampler, because there's so much padding on the edges that we are now our new image will actually be larger, right? And you can sort of see visually this effect here. We added like 2 pixels of image, 2 pixels of padding around this 2x2 image, and our upsampled version is actually larger. And then with different kinds of strides, you can further upsample your image. Right. Deconvolution. All right, thoughts, questions on these two approaches to upsampling? We're going to like lean on these two to sort of give us the granularity in images that we want. We also discussed like conditional labels previously, and you might ask, how do you introduce conditional labels when we're doing upsampling with these various approaches? Well, first of all, with the discriminator, we've already, this is more straightforward. What we can do is we want to force our additional information, this label, to be something that looks as similar to or cohesive with this image, or like raw image as possible. And so one idea for doing this is that we're going to sort of think of each label or vector as just being a feature map where it is a 1x1 image and the channels reflects the dimension of the latent. And then what we'll do is we'll turn it into something that looks like the width and height of the original image, and then just add that along the channel dimension. Right, and you might imagine that maybe you don't want it to be the size of the original image. You can downsample the image first, but this is how you can add an additional latent to the input. Right, so the discriminator gets access to this latent via something that looks like just enhancing the image and adding more dimensions to it. Thoughts, questions on this? Cool. This solves the problems on the discriminator side, where we want to give the discriminator some information about what we expect the label to be. On the generator side, it's also a little tricky, or we can take similar ideas. First is that we have some kind of latent vector that's on some low-dimensional space. We could just tack on the label in addition to that, and sort of just hope that this all works out, and that this sort of captures and gives all the information that we'd like. There's probably some smarter ways you can do this, right? So similar to the previous idea, we could first upsample our latent, and then also upsample, process the label, and then concatenate them in a way that we discussed previously. So maybe it's down the line that we choose to actually combine these two, and then resolve it to an image. Cool. Nice. Glad everyone understands. Questions about our basic setup for most image generation tasks? Not? That's awesome. All right. So our first version of this traditional GAN that we'll discuss is called style GAN. These sections generally are meant to give more insight for people who are interested in architectures, thinking from the perspective of a machine learning engineer who wants to build custom models to achieve different tasks or to like improve different aspects. And there's style GAN is a complicated but good example because it tries to achieve a couple of improvements at the same time. And we'll see that it does it in pretty interesting ways. So in particular, we have 3 desiderata from style GANs. The first is that we have an intuition that latents might have more granularity or interesting representations than just a sort of like multivariate normal or Gaussian that we might traditionally have. For example, we might think there's different aspects of our latent space that encode different kinds of features, and maybe we want to be able to decompose that when we think about latents in practice, right? That might sound abstract, but basically just think like latents obviously capture different aspects of the information about an image, right? Some might encode like what is in the object, some might encode what is the background and so on. And there might be some way to like think about how do I separate those and get different levels of representation. A second idea is that when we're doing the upsampling task, when we're generating, more granularity in our image, perhaps we want that to continually have access to the latent, so we can continue to steer this generation process towards an image that matches and coheres with our latent space, right? Because you might imagine that if we just take this original latent and then pass it through different levels of upsampling, maybe by the end you've like missed some important information and granularity that was supposed to be there. And so it might be useful to have the information possessed by the latent to be passed into each step of upsampling or convolution. The last thing we might have an idea for is that textures are important and have a unique function in that they require some level of randomness to seem photorealistic. And in practice, many things in the real world are, like fundamentally, basically random. You might imagine like hair, as you can see, like on the right here, is pretty random and requires that you like have to generate things like waviness. Other things in practice, like let's think like waves or like the motion of fluids might look genuinely random at a really granular level in a way that requires like some kind of randomness to look like it is realistic. Okay, we're going to walk through our architecture decisions that help us achieve these. But again, let me know if you have questions. Here's the architecture we're going to use. I know it looks like it's a big jump scare moment up front, but we're going to unpack each stage. On the left here is your traditional GAN. So this should look somewhat familiar, but the idea is you go straight from a latent to your image through blocks of convolutions and upsamplings with normalization. And on the right, we have the style GAN architecture, which we're going to break down piece by piece. Okay. The first thing to notice is that there's still this sort of a similar upsampling block, which occurs in both architecture. With the idea is that you have these upsampling convolution, normalization blocks at its core, with some modification that we'll discuss for the style GAN. But you can think of each of these as being the upsampling step that we talked about previously, right? It introduces, it lets us enlarge the image and get closer to our final output. But otherwise, in principle, is the same. And so what's left is to think about what is different, which is this step here, and then these sort of things that we seem to be like adding into this setup. So let's look at this first piece. We first stated that we wanted to have pre-processed latents. And so what we're going to do is introduce more complexity and let our latents capture more interesting information with this MLP, which essentially just is designed to encode and get to capture different information from our latent space. The idea is that we might not be able to do this if we don't process this into a more intermediate, like higher dimension latent space, right? And the idea is you should think that like W is higher dimensional than Z here. Cool. These latents are then incorporated into each of the convolution steps via something we call adaptive instance normalization. The idea is that there's some normalization and processing that we'll do built into our conventional like batch norm that will allow us to input information from our latents, from these like latents that I've just processed. You should think of it as sort of like an affine transformation, if the word's familiar, but it's rescaling and rebiasing, right? So recentering and then scaling it up. We've also discussed that like we want our convolutions to incorporate latents, and this is the step where that occurs. Right, we're able to decompose each aspect of this new latent that we've learned and incorporate it at each step of convolution via these norms. And so throughout this synthesis process, we're continually steering the generation with the latent that we've created. Cool. This is quite interesting because you might immediately think that like, hey, this is not a very big difference. You're only like rescaling and rebiasing, which seems like just two changes. And in fact, this is actually like pretty surprising and remarkable. That this is sufficient in and of itself to steer towards something that's like similar to the original image and encapsulates a lot of information. The authors sort of say like, hey, this is like kind of weird that it works, but like shrug. I guess it works. It's good. Yeah. But in some other sense, like, we can also intuitively explain why this should be okay. If we have a like high fidelity latent space, it's able to capture a lot of information. And at each step, we're able to, across multiple generations, we're able to like incorporate the relevant information. Then you might expect that this like eventually does get us to where we want. Cool. The last sort of piece here that we've changed, while the A's that we're incorporating here are the latents, the B's are just random noise, just actual randomness, where the idea is that you add a little bit of Gaussian noise, and that enables the network to learn that has access to this randomness and use that randomness to generate different features that it might want. And so the idea is that if we're giving this network some noise, then it should learn that it can take advantage of this noise to, let's say, learn the pattern of like hair, or learn how to turn that into like a texture for hair and generate more realistic images. I think in particular, like the change that you should notice is that you go from something that looks much more like blurry hair here, which you might think is just what you would get if you didn't have access to randomness, to something that looks more like A, right? Where it's obviously more similar to real hair.
Sorry,
yeah.
For these pictures on top, is one like sent to the other, or what exactly? Can you explain why exactly the splitting images and what each image is in terms of what produced by the staffing?
Yeah, that's a good question. I want to say, yeah, my intuition is that the ones on the left side are going to be the ones that have access to noise. And then the ones on the right side, I'll have to get back to you. I think it's brought up in the paper, but we'll check that right after lecture and let you know. Good question, though. All right, Neshi, could you check real quick? That sounds good. Cool. Nice. Yeah, good question. But to summarize, what we've done here is that we've discovered a better way to incorporate the latent vector. Our adaptive instance normalization, or ADA-in, block lets us influence the generative images at each step of upsampling, and the randomness lets us like introduce better texture and also control whether that texture is on or off. Here's some random factoids if you're interested in learning a bit more. There's also improvements on StyleGAN. Beyond StyleGAN 2, there's now StyleGAN 3 and 4, 3, and I think other improvements that generally try to improve these models by adding like more deep learning tricks. If you're interested. Cool. So here, what we generally wanted to do is to create more photorealistic images, things that are more convincing. This next session we're going to talk about introduces a different kind of task or a goal, where in particular what we want to be able to do is sort of convert between different styles or pairs of images, where you can see here that some conversions we'd like to be able to have are turn from paintings into photorealistic images, turn from zebras into horses, and so on. The idea is that like in each of these, there are some very core similarities in the content of the image, right? In each of these images, like if you sort of squint, they look very similar. and instead be able to like easily layer or swap between these sort of like modes or labels, right? That like the core content or like subjects of the images are the same and like have the same geometries and so on. This might seem like a pretty tricky task to be able to accomplish, right? Because what we want to do here is have a network in which we can take an image that is like clearly a zebra and then generate it by swapping the label to be a horse, and then get the same similar looking image, except like skinned as a horse, let's say. Here's the architectural solution. The idea is that we still have our discriminator loss, but there's also a new loss function that we add on to the discriminator loss that we will call cycle loss. The idea is that we want at our core to be able to turn our image from like A to B and then B to A and still have that cycled version look similar to the original, right? If I have a horse image, then I turn it into a zebra. I want this model to then be able to turn the zebra back into a horse and have it look similar to the original. I think this captures sort of like the intuition for what we want, which is that we don't want to affect the substance of the image. We sort of want all the objects, geometries, etc., to be similar. It's just this one piece that we'd like to change. Formally, what we do is have these two generators that we perform this sort of conversion function, and then we just impose this loss function, which is like suppose we convert A into B and then A again. How different is that from the original? And similarly, suppose we turn like B to A to B again. How different is that from the original? And that completes the cycle both ways. All right, questions, thoughts? Yeah. Yeah, that's a really good question. And you'll be right to observe that, yeah, like in the autoencoder, you have an sort of like you encode to a latent space and then decode to a like back to your original, and then you hope those are similar. And I would agree that like this is pretty similar. The main thing is that in an autoencoder, like you're downsampling to like a latent space and then going back up. Whereas here, the like intermediary is another image, right? And I think otherwise it's like basically like perfectly analogous. Oh, and maybe one of the differences is that you want it to be, you have a sort of symmetric loss thing where it's not only that you want to go from A to B to A, but also from B to A to B. B to A to B would obviously is not something that you want in autoencoder necessarily, but it would probably be pretty trivial. Yeah. Cool. Thanks for the clarification. All right, other questions? Cool. For those of us drawing ideas that we want to be able to convert between things like zebras and horses, and so we'll impose a like cyclic loss that captures what we want, which is this preservation of like objects, geometries, etc. Here's what that ends up looking like in practice. In this video, we're taking an image, like a video, and then converting each frame via this like cycle GAN. And you can see that it produces like pretty convincing footage, although like with maybe some like strange dancing of the zebra's patterns. But that otherwise like seems more or less like you've changed a horse into a zebra in a decently convincing way. Cool. All right, a final and third architecture that we'll discuss is big GAN. The idea is just that like we want to examine behaviors of generative adversarial networks as you scale them up, both in terms of the amount of training data as well as the difficulty of the challenge. And in particular, we're using ImageNet, which has 1,000 classes and like I think like 10,000 instances of each. And so much harder challenge, also much more data. And we want to know how different choices about the architecture can end up influencing its downstream performance. Cool. Some laws discovered when we just throw like like different versions of GANs at this issue, this problem are that if you have a bigger model or more data or bigger batch sizes in each update, then you'll do better. And just generally, like this is like not very surprising that these things are almost always good. And in particular, batch size seems to play an important role in the stability of training. And that if you update not on one image at a time, but let's say like 16 images or 64 images, then each individual update will be like more stable. There's less bouncing around, and this should make sense, right? Whereas like one image is a pretty noisy update. If you are updating for multiple images at once, then that's probably like going to be better. Yeah, you should note that this is like pretty, like especially good for us because we think that GANs are very unstable and hard to train. And it turns out this like batch size parameter helps, gives us a lot of like leeway. Another interesting, a big interesting thing that came out of this paper is that there's a truncation step that you can perform test time that improves your performance. Normally, we think of our latents as being like adhering to some either like normal distribution or uniform distribution, and this might not always be what you want. First of all, like for uniform distribution, it's just is not the case that like all samples are equally likely, and so it might not be able to like encapsulate what we want out of a latent space. A normal is better, but the problem with the normal distribution is that there's always some probability mass at the extremes. We'll eventually sample like a 3 z-score data point, and so sometimes our model will just do really poorly, and we might not want that, right? So here's a standard normal. I think like outside of this like 2 standard deviations, you'll still have 5% of your samples, even if these are like pretty unlikely or like strange items. And so one way to fix this is when you're testing and evaluating your model, what you'll actually want to do is just cut off or truncate this normal distribution so that it doesn't generate samples that are more than X standard deviations away from the mean. Right here, like these red boxes roughly correspond to 2 standard deviations away. It's like 5% of the mass, and you can parameterize around that cutoff. This gives us more control over 2 things, I guess. Like the trade-off is between your ability to generate diverse images, right, by being able to access more like different parts of this latent space, but might improve stability in the process by making the model only learn from more realistic or like common images. And here's an example of how you can visually see the effects of this truncation parameter. Well, you might notice that when we set our truncation threshold to be something high, like 2, right? And so we're including everything within 2 standard deviations here. You still get like a lot of like interesting, maybe like degenerate images. Like some of these dogs don't look very good. But if you reduce that truncation parameter to be something that's really low, like 0.04, you're basically like just including the mean plus like a tiny bit of variation. Then in fact, like the images you generate will also similarly be extremely similar to one another. Right. And somewhere in between is maybe the sweet spot you want. If you have poorly conditioned generator, in other words, like a generator that doesn't handle distribution shifts very well, then you can also have like weird effects that look like saturation you can see in B. But some tricks like regularization can get you where you want. Yeah.
I don't understand why, let's say when you truncate, right?
Mm-hmm.
Right?
Yep.
And what I thought was happening was by doing so, you basically reduce the chance, you get rid of the possibility of getting your generator a latent that's not actually been trained on as well.
Yep.
Having the probability of the sample. But why is that? Well, first off, what does probability exactly mean in the sense of why would changing the probability density of the latent change the behavior of the generator?
Why would changing the probability distribution of the latent affect the generator behavior? I think the idea is that like your generator Yeah, I mean, I guess I think the idea is that like your generator hasn't learned. Okay, I think I can give you a better explanation later, maybe. And I think this is a good question. I think the way I explain it is just that like if your generator hasn't learned to has learned like a strange distribution or ones that like might not adhere or like assume a sort of normal distribution, it's gonna be like, sorry, this is gonna like sound like this is not gonna be a good explanation, I guess. Yeah, let's talk about after. I think the big picture though is that like if the generator doesn't like isn't like assuming or sort of like understanding that like the normal distribution is the distribution is like normal in the sense that these are extreme cases, we want to be able to like learn assuming that these are outliers, then you might get unexpected behavior when like you take off or like cut off some parts of the distribution. They might have assumed that those have like higher mass than they like you might actually want in practice. And yeah, I think generally like that might mean that like when you shift the distribution, it could behave like unexpectedly in some way. But yeah, bad response. Let's talk about after. Cool. But yeah, hopefully this previous image just taught you that more constraints introduce stability at the cost of diversity in the images that you can generate. Cool. All right, other questions, thoughts on this stuff? Nice. I'll quickly mention that with big GANs in particular, there have been more interesting recent developments. You've probably heard of stable diffusion before. And if you haven't, then it's sort of the thing that drives or powers a lot of the more interesting and powerful image generation models. If you've used like DALL-E or something, like that's probably a stable diffusion model underneath the hood. And you might get the impression that like stable diffusion is just a direct like improvement on GANs, and it's just like where the research community is headed. It is true that like stable diffusion is like really powerful, and we'll learn about it in a later lecture. But more interestingly, there's been recent research that shows that a lot of the benefits or the improvement of stable diffusion's algorithms are actually like driven mainly by just massive upscaling and training data. And in fact, if you take like a GAN that has like some good architecture decisions and you just throw a shit ton of data at it, it can actually perform comparably to state-of-the-art stable diffusion models as well. And so there might be a case to be made that like the main bottleneck is data, and that GANs are a fine architecture still for condition generation. Cool. All right, let's just like summarize like some things we've learned about these three different models. If you want something that's more photorealistic, things you can do are like make your relations accessible and feed them in throughout the process, as well as give access to random noise. We've talked about CycleGAN, which lets you lets you do this sort of like swapping process. We swap in zebras and horses, and adding interesting losses can let you adapt your GAN to different tasks. And then finally, by talking about some like really big GANs, we've learned that like bigger batch sizes help introduce stability, and it's quite good for training. And sampling from a truncated distribution might get you like good test time results in the future. And in particular, there's probably like some sweet spot for discriminator power. You don't want to like collapse your model, but if the discriminator isn't very powerful, you don't know anything at all. And so all these parameters are something that you have to like toggle around and adjust in practice. Cool. All right, here's the lecture attendance link. Feel free to fill it out now. I'll leave it up for a second. If you do have questions, me and Arian will stay around for a bit after, and Arian will probably be more of use. Great. Yeah, thanks for everyone for coming. Hope this was interesting. Oh, yeah, yeah. I mean, I think there's a lot of interesting variants. Okay, I'm gonna ask Arian after, but I think